Problem number 13. Find the sum of the telescoping series, the sum from n from 7 to infinity of 2n plus 1 divided by n squared times n plus 1 squared. So telescoping series means that we need to have our terms cancel out. We need to probably have like one fraction minus another fraction, so we have lots of cancellations between the fractions. That's what we're looking for in a telescoping series. But we don't see one fraction minus another fraction here, which suggests that we need to rewrite this. So how do we rewrite this? We're going to rewrite the individual terms that we're adding up here, and we're going to rewrite this using partial fractions. So partial fractions isn't just a method that will allow you to evaluate integrals like we did earlier in this course. It also allows you to rewrite terms of series here to get them all set up so that we can see it's a telescoping series. Okay, so let's get to work here. We want to find a partial fractions decomposition of 2n plus 1 divided by n squared times n plus 1 squared. And so we're going to rewrite this as, so I see we have an n squared in our denominator. So we need an a over n and a b over n squared term. We also have an n plus 1 squared term in our denominator. So we know we need a c over n plus 1 and a d over n plus 1 squared. So this is the setup, this is the recipe, the format, the pattern, all of those good words used there for our partial fractions. Now our goal is to figure out what a, b, c, and d are. So first we multiply through, clear out all of the denominators. 2n plus 1 is equal to, so this will give us a times n plus 1 squared, plus b times n plus 1 squared, plus c times n squared times n plus 1, plus d times n squared. And that's what we get when we clear out the denominators. Okay, so our goal is to figure out a, b, c, and d. There's several different ways to do this. I'm going to start off by plugging in appropriate values of n to solve for a couple of the variables, a couple of the constants very quickly. So if I plug in n is equal to 0, I'm going to get 3 of these terms on the right to be 0. This will be 0 because there's an n squared. This will be 0 because there's an n squared. This will be 0 because there's an n squared. And so the only thing that will be left here will be a b times 1 squared. So that's just b. And on the left here, 2 times 0 plus 1 is 1. And so we conclude here that b is equal to 1. Okay, so I got rid of the terms with n in them by setting n is equal to 0. 3 of the terms have a factor of n plus 1 in them. So I want to make n plus 1 equal to 0. Well, I set n is equal to minus 1. So this will go to 0, this will go to 0, this will go to 0. 0 plus 0 plus 0. And then d times minus 1 squared will be d times 1, just d. And on the left, we'll have 2 times minus 1 plus 1. Minus 2 plus 1 is minus 1. So minus 1 is equal to d. Okay, so far we've got 2 constants down and 2 to go. Okay, so next up we need to figure out a and c. And there's a couple of different ways that we can do this. I'm going to choose to expand out the multiplication. I'm going to expand all of these expand all these products out. And so then I'm going to be able to compare coefficients on each side. So let me go to the next slide so I can expand everything out. So 2n plus 1 is going to be a times n cubed plus 2an squared plus an plus bn squared plus 2bn plus b plus cn cubed plus cn squared plus dn squared. So this might look nasty. All I did here was rewrite this, multiplying out those three terms. Okay, so what do I do with this? I'm going to look at coefficients of different powers of n here. So first I'm going to look at the coefficient of n cubed. So on the left, the coefficient n cubed is 0. On the right, it's going to be a, not n cubed, not n cubed, not n cubed, not n cubed, not n cubed. We have a c, not n cubed, not n cubed. So here we have an equation. A plus c is equal to 0. That tells us a is equal to minus c. Okay, so that doesn't tell us yet exactly what a and c are, but let's look at the coefficient of n squared here. So the coefficient n squared on the left is, again, 0. Not n squared. Oh, there's a 2a here. Not n squared. There's a b. There's a c. And there's a d. But we already know b is 1 and d is minus 1. So we have 2a minus 1 plus c minus, 2a plus 1 plus c minus 1. The plus and minus 1 cancel out. So that 0 is equal to 2a plus c. Okay, well, what can we do with this? Well, a is equal to minus c. So that means we could replace a with minus c. That's minus 2c plus c. Well, that is equal to minus c is equal to 0. So that tells us that c is equal to 0. And because a is equal to minus c, that tells us a is equal to 0. So now we have all of our constants here. So we are now looking at the sum from n from 7 to infinity of a over n, well, that's 0 over n, we don't have to write that, b over n squared, so that's 1 over n squared, plus c over n plus 1, so that's 0 over n plus 1, so we can drop that, plus d over n plus 1 squared, and that's going to be minus 1 over n plus 1 squared. Something that's worthwhile to do, I won't do it in this video, but you can always double check that you did your partial fractions correctly by combining this together and making sure that you do get 2n plus 1 divided by n squared times n plus 1 squared. Okay, so this is where we are at. So we've done all the crunch work here, and now we're going to get to the telescoping series part of it. Everything up to here has just been partial fractions. So what happens now? Well, we can see that things are good here, that we actually do have a difference of two terms here, and so we can see that, yes, our terms are going to cancel here. So we just write out the first several terms. When n is equal to 7, something to be careful with, this is not starting at n is equal to 0 or n is equal to 1. Starting at n is equal to 7, we're going to get 1 over 7 squared minus 1 over, 7 plus 1 is 1 over 8 squared. When n is equal to 8, that's 1 over 8 squared minus 1 over 9 squared. When n is equal to 9, this will be 1 over 9 squared minus 1 over 10 squared. And we can see that we're going to get cancellation here. We're going to get 1 over 7 squared minus terms where the denominator is getting ever bigger and bigger and bigger, which means that those terms are going to 0. So that says here that this is going to be 1 over 7 squared, which is 1 over 49. If you want to see a more formal way to do this, we can do this using partial sums. So S sub 7 the partial sum of all the terms up to the n is equal to 7 term is just 1 over 7 squared minus 1 over 8 squared. S sub 8 is 1 over 7 squared minus 1 over 8 squared, plus 1 over 8 squared minus 1 over 9 squared. S sub 9 is 1 over 7 squared minus 1 over 8 squared, plus 1 over 8 squared minus 1 over 9 squared, plus 1 over 9 squared minus 1 over 10 squared. Cancel, 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 cancel. So we see S sub 7 is 1 over 7 squared minus 1 over 8 squared. S sub 8 is 1 over 7 squared minus 1 over 9 squared. S sub 9 is 1 over 7 squared minus 1 over 10 squared. So our general formula for S sub n is 1 over 7 squared minus 1 over something squared. When n is 7, there will be 8. When n is 8, there will be 9. When n is 9, this will be 10. So that will be n plus 1 squared. And then the limit as n goes to infinity of S sub n is sure enough going to be 1 over 49, because that's going to 0. So that's an alternative way to derive this.